Talking about symmetries, we have been involved in such exercises where we are talking about symmetries right now, and and what symmetry basically means that symmetry means the invariance. I mean the invariance, the invariance of a system under some transformation. Now, for example, if I take an example of a spherical ball, and this spherical ball is rotated. Suppose it's a ball, and this ball is rotated. Now, this ball will look like same no matter how this ball is rotated. So, what am I trying to say here is that this symmetry is a powerful tool. It's a very strong tool to investigate and to understand the behavior of elementary particles. And there exist the relationships between symmetries and conservation laws. And conservation laws. And in particle physics, we call them Noether. And this is what I'm trying to say here is that symmetry basically it leads to the conservation laws. And in classical physics, we have the relationships between the symmetries and the conservations. And the very first example is the invariance. If we have invariance under translation, invariance under translation. This invariance under translation, what it leads to the conservation of linear momentum. And similarly, the invariance under the change of time, invariance under change of time. What it leads to the conservation of energy. It leads to conservation of energy. And then we can also talk about the invariance under rotation. If we have a system and we have invariance in rotation. And this invariance in rotation automatically leads to the conservation of angular momentum. Conservation of angular momentum. I mean, in particle physics, there are many examples of symmetries and the conservation laws that are linked with those symmetries, that are associated with those symmetries. I mean, the examples like permutation symmetry. Permutation symmetry. Now, this permutation symmetry, what it does basically, it deals with the symmetry of the system under the exchange of the particles. Exchange or permutations of the identical particles, and it automatically leads to what we call as Fermi-Dirac statistics. And the particles that we have here, we call them as fermions, and Bose-Einstein statistics. And the particles that we have here are bosons, and we have continuous symmetries, and we have continuous symmetries. Now, what continuous symmetries deal with Here this continuous symmetry deals with the symmetry of the system under infinitesimally small transformation. For example, the symmetry of a system under small rotation in space. So this is what's called as continuous symmetry in particle physics. And then we have another example of discrete symmetry. Discrete symmetry. And what it does, it basically deals with the symmetries of a system under operation which exists in the form of stubs. And for example, we can have an example of parity here. Parity, where we have space inversion. And we can talk about charge conjugation. And time reversal. So these are the examples where we have discrete symmetries involved. So this was a small introduction of symmetries. Now the core thing is basically that we want to talk about SU2 symmetry. Now, to start with, we have protons and neutrons, and between these protons and neutrons, there are a lot of similarities between these particles. I mean, between these protons and neutrons, there is strong nuclear force, and this strong nuclear force is responsible for holding this proton and neutron in a nucleus. And in a nucleus, what we have, we have charge independence between these two particles. I mean, the nuclear force that exists is the strong force between this proton and neutron does not depend on charge. So what it means here is that nuclear force between these pairs that we have, proton, 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 neutron, and neutron and neutron, the magnitude of this force is same for all the three combinations. And now, however, at the same time, there's a small difference in the mass of this proton. And if I have to numerically write down the mass of this proton in terms of mega electron volt per c squared, and this is nearly 938.28 mega electron volt per c squared. And the mass of the neutron is 939.57 mega electron volt per c squared. So now there is a slight difference in the mass of the proton and neutron, and this is probably due to the electromagnetic interaction. Electromagnetic interaction, or the interaction that's arising due to the charge content that we have in the proton, and we also have the charge content in the neutron. No doubt the total charge of the neutron is zero, but that zero is made of some kind of frictional charges that are there inside the neutron. So there is an electromagnetic interaction between the charge of proton and the neutron. And this small difference in the masses of these protons and neutrons are because of this electromagnetic force or the interaction that we have here, and that this interaction is coming due to the charge content that we have in proton and neutron. And proton has a positive charge, and neutron, the overall charge of the neutron is neutral. But if somehow this electromagnetic interaction is switched off, say hypothetically, if we switch off this electromagnetic interaction between the proton and the neutron, then according to Heisenberg, this proton and neutron they are identical and they are indistinguishable particles. So to say, it means that protons and neutrons are identical particles. They are collectively known as nucleons. Under strong interaction, if we switch off the electromagnetic interaction between the proton and the neutron. So proton and neutron, they are basically the two states of a particle known as nucleon. So, I should say that it's possible to imagine a group of symmetry operators which could transform a proton into a neutron, and vice versa. In absence of, see, we are switching off the electromagnetic interaction. So in absence of electromagnetic interaction, this proton and neutron, they form the fundamental representation of a group. And the existence of such a symmetry, it certainly does imply that something remains invariant. Something remains invariant, or you may call it constant, in the nucleons under this strong interaction. Under the strong interaction. Now, this something we have already introduced. This something is known as isospin, and it is symbolized as I. And this I is analogous to the spin S that we have, and the value. And what we have here is that we have 2I plus 1 discrete orientations, or discrete values, or we may call them degenerate states. Degenerate states. So we have this something, and this something is isospin, and it has 2I plus 1 degenerate states. And this degeneracy, we call it as multiplicity here. With the third component, what is that? That's I3. And this third component of this isospin, which we have already discussed in the isospin quantum number. And what we have here is we have I and we have I3. Now, the value of this I3, what it does, its value ranges from minus I to plus I. And are separated by the number 1. Now, for nucleon, if we have a nucleon which has I equal to 1 by 2. So to say, there are two particles in the multiplet. So what are they? That they are 2I plus 1. So they are 2 times 1 by 2 plus 1. That's going to give us 2. Now what are they? They are proton and neutron. And so isospin is 1 by 2 for both proton and neutron. With the third component, now with the third component, I3 is plus half for proton, and this I3 is minus half for neutron. Now, thus we can say that the operators of symmetry group, what they do is the operators of symmetry group change the coordinates of the isospin in such a way to reverse the sign of this I3. To reverse the sign of this I3. That's the conversion of proton into the neutron, and the reverse is also true. Now, if the strong interaction or the strong nuclear force is invariant under rotation in the isospin space, then according to the Noether theorem that I simply stated, the Noether theorem, isospin is conserved. Isospin is conserved. in strong interactions. And isospin symmetry, what it does basically, it reflects in the physical state. It reflects in the physical state that belongs to the isospin multiplets, and which have the same mass. Hence the proton and the neutron, which is basically a nucleon doublet that we are talking about, have same mass due to the strong interaction. They have the same mass due to this strong interaction. They have the same mass due to the strong interaction, and due to this isospin. And what isospin symmetry we have here? We have we call this SU2 symmetry. Now, to state the same thing in some simple way here is that this SU2 symmetry, what it does basically, it identifies. It identifies what it identifies. It identifies the proton and the neutron, as the different states of the same particle. And what's that same particle? That same particle is a nucleon. That same particle is a nucleon. And this SU2 symmetry, it's a 2 by 2 unitary matrix with the determinant, with a unit determinant. Now, this unitary matrix U, as a function of, say, theta 1, theta 2, and theta 3, is given by e to the power of minus I theta j and sigma j. And the j that we have here, this j can have the values of 1, 2, and 3. And this sigma that we have, sigma j, they are known as Pauli matrices. And these Pauli matrices, as we know from the foundation of quantum mechanics, these Pauli matrices that we have, the better thing is to write down this equation. We have a unitary matrices given by e to the power of minus I theta j and sigma j. And this j is 1, 2, and 3. And sigma j, we call them Pauli's matrices. And for sigma j, what we have sigma 1. And what is that? That is 0, 1, 1, 0. We have sigma 2. That is 0, minus I, and 0. And for sigma 3, we have 1, 0, and 0, and minus 1. All right. And the theta j that we have here, they are the angles of rotation. Theta j, they are angles of rotation in isospin space. Isospin space. The fundamental particle doublet that we have in this SU2 symmetry is two-dimensional, which is given by the two components of the column matrix. Therefore, if we write down a nucleon as a two-component column matrix, suppose N refers to nucleon. And what it is, this nucleon is a column matrix with alpha and beta. And with proton, we have 1 0 column matrix, and for neutron we have 0 1 column matrix. And on these proton and neutron, the Pauli's matrix matrices can operate. So these Pauli's matrices can operate on these protons and neutrons. Now, this isospin symmetry, it's broken by electromagnetic, and because it's violated, it's a violation for weak interactions. I mean, this isospin symmetry, what happens here is that it's crushed by electromagnetic and weak interactions. Electromagnetic and weak interactions. If we rightly remember, we started with an assumption that we switched off the electromagnetic interaction between the proton and neutron that led to the strong interaction alone between these nucleons. And the result of that was that these proton and neutron, they're identical particles with two different quantum states. Now, breaking the isospin symmetry allows us to distinguish between the proton and the neutron. So when we switch off, when we switch on this electromagnetic interaction, what we have here is that the breaking of isospin symmetry, what it allows us is it allows us to distinguish between a proton and a neutron. And at the same time, it must be pointed out that electromagnetic interaction conserves what it conserves the electromagnetic interaction. It conserves the third component of isospin. It conserves I3. And taking an example of pions, say for pi mesons or pions, for pions, what we have, I is equal to 1, and what about its multiplicity? That multiplicity is given by 2i plus 1, so that is 2 plus 1 equals 3. So we have three states of pions here, and these three states are pi plus, pi 0, and pi minus. What they do is they form a triplet. They form a triplet, and the three pions in the isospin space, they can be written as pi plus is 1, 0, 0 matrix, pi neutral is 0, 1, 0 column matrix, and pi minus is 0, 0, 1 matrix. And the strong interactions, they treat three pions alike. They treat them same, and what they do is they conserve the isospin.